Good morning, everyone. Welcome to today's session of India Webinar Series Introduction to Computational Drug Design, co-organized by Schrodinger and PCI. I'd like to thank our collaborators for supporting this event. Before we move on to today's session, I would like to make a quick announcement. There has been slight change in the schedule for this week's session. For the updated schedule, you can visit our website, the website page for this event, which is schrodinger.com/dd course. If you have any questions, please do let us know. So today's session is another demo session on molecular dynamic simulation and trajectory analysis, system preparation, simulation analysis, simulation interaction diagram by Dr. Kaushik. During this course of presentation, if you have any question, please feel free to drop your queries in the chat section of the YouTube link. We will have a Q&A session at the end to answer your questions. Without further ado, I'd like to welcome Dr. Kaushik.
Thanks, Sylvia. Can you hear me?
Yeah.
Perfect. Can you see my screen too?
Yes, I see your screen.
So a very good morning to all of you. 3 weeks back, we discussed MD theory and how to analyze MD simulations using Schrodinger. Today, we're going to have a hands-on demo sessions on how to set up the calculations, how to run the simulation. And if you remember from our presentation 3 weeks back, I showed you this video where you have the ligand in here and you have a protein. You're trying to see how the ligand interacts with the protein during the course of simulation. So today we are going to go into details of how to set up the calculation, how to run the simulation, how to analyze the simulation. So without giving you any more slides, I'll just move to Maestro after this. Just give me a second. So can you see Maestro? Can someone confirm?
Yes.
Perfect, thank you. So the first thing that you have to do by now, you should be aware of, is that whenever you open a new project in Maestro, you have to go to File, you click on File, and you go and change Working Directory. So in the Working Directory, I'm going to create a new directory for this one. I'm going to call it as MD Simulations. Okay, and I'm going to choose that as the working directory. The next thing that I'm going to do is I'm going to save the project. So I'm going to go to File, Save Project As, and I'm going to save it as MD Simulations. So now that I have done it, the next thing that I'm going to do is I'm going to import and process a protein. By now, all of you should know how to import and process a protein. You go to File, you go to Get PDB. The PDB ID I'm going to choose for this particular session is 3LAU. Okay, so the PDB ID that I'm choosing for this session is 3LAU. I'm just going to click on Download. And automatically the protein loads up in the workspace. Now you can directly go to protein preparation by clicking on here. You can click on here also if you want to go for protein preparation, or you can go to Task, Browse, and go to protein preparation and refinement, and you can do that too. But before I want to do that, I just want to look at the protein once. It's always a good thing to look at the protein before you do the protein preparation. So I just use this position here, and you can see that you have the protein here, and you have a ligand here, and you have these red spheres that are water molecules that are present here. And you can see that the water molecules are only red spheres. You don't have any white bonds formed next to the red sphere, which indicates that there are no hydrogen in the system. So you should add hydrogens also. So this is just a brief overview of the system is. And the next thing I want to do is I want to go and prepare the protein. So I'll just go to protein preparation wizard, which is over here for me. You should also be able to find the protein preparation wizard here. If not, you can always go to task and you can just go and search for protein preparation. So let me just open the panel. So for this exercise, I'm just going to select all the options here. It doesn't take long to fill this up. It will probably take around 1 minute to pre-process the whole structure. You don't have to do this, but when you do MD simulations, it's usually recommended to make sure that you have all the sections present and you have all the missing residues present also. So I did select this options of fill missing sections using prime. and also selected this option of filling missing loops using prime. And the rest of the stuff is something that I'm just doing this for protein, doing it for this protein because I know what this protein is. But for your system, it might change depending on what you're trying to study. So I'll just click on pre-process, and you can see that the job starts here. It's going to show you a pop-up menu, which is asking you if you want to continue to fill the missing loops with prime. And I want to do that, so I'm just going to click on continue. This job is going to take around 1 minute. Let's just wait for it to finish. And again, just to remind you, if you have any questions or if I'm going a bit fast, let me know in the comment section and someone can relay the information to me from the YouTube comment section. So we'll just wait for the job to finish, and it's going to take like 1 minute. You can see that the prime job started. If you want, you can go and monitor the job here. Go click on jobs, go to see, you can see that the job is running. It's trying to fill the missing loops. You can click on monitor. And it opens a panel that is here. You can click on the job. You have log files. You have other files here. You click on the log file. You can see the log file being displayed here. Right now, it is mostly all you have is basic information. It hasn't yet done the calculation. It's going to do it soon. It's going to finish in like half a minute or so. I'll just close this panel and I'll just wait for it to finish. So far, all we are trying to do right now is just make sure that you have the right bond orders for all your the ligand and the protein in your NT, in your workspace. We added hydrogens to it. If you have a metal, then we're going to add zero order bonds to the metals. But we don't have a metal in the system, so we don't have to worry about this. But choosing the option does not harm you. If it's there, it's going to add it. If it's not there, it's just going to leave it. It's also going to create disulfide bonds if you have cysteine residues too close to each other. Now it says the missing loops have been incorporated, has been completed, and now you have the epic job being run. And so once the job finishes, you should see this structure, which is named as pre-processed. Okay, this will automatically load into the workspace. You can see that the structure has loaded into workspace. You can see that there are no water molecules anymore. There are no red spheres anywhere. You can also see that if you zoom in, you can see that all of these atoms have white color lines here, which indicate that hydrogens have been added to them. And so the next thing that you want to do is you go to the refine step. You might go to review and modify if you think that there are other things, but I know the system, so I don't want to waste time on review and modify. I'll just go to refine directly. And once I go to refine, there are a few options that are here, and you should be aware of this from the previous sessions. So the first thing that you have to do is assign the hydrogen bond for your system. So in the previous step, you added hydrogens, and now you're trying to make sure that the hydrogen bond assignment is proper, depending on the pH of at which you want to run the simulation. So I just clicked on optimize, and you can see that the protein assignment job started. You can monitor the job here at the job section. And so let's just wait for it to finish. It's going to take somewhere around half minute to 1 minute. If you want a finer control over your hydrogen bond assignment, you can go to interactive optimizer. But as you can see, the job finished, and I have a new molecule loaded into the workspace, which is 3LAU H bond opt. Okay, I'm going to go back to my protein preparation wizard. And you can also see that it labeled all of these things, HIE, HID, where it tries to assign the hydrogen bonds to the histidines. But you can turn off these labels here. Let me just go back to the protein preparation wizard. And the next thing I want to do is, I already removed the water, so I don't really have to do this step, but it doesn't really harm to do this step. So I'll just click on this. And you can see that because there are no waters, it processes this step really fast, and it loaded removed waters here immediately. So the next thing that you want to do is you want to minimize the structure. And so you have two different force field options here, OPLS3, OPLS 2005. 3E is the most recent one, so try to use 3E. And then you click on minimize, and you're just going to wait for the minimization to finish. It's going to take around 1 minute to finish the minimization, so let's just wait for it to finish. You can always monitor the job here. You can go to jobs. You can check the jobs that are completed. You can check the jobs that are running right now. I'm going to click on the running one. You can check the log file here. You can see the information here. So you can do all of these things. If this job fails, you can always go to the postmortem, click on postmortem here. You can check all of these options and create a report and send the report to us if you have any issues in your calculation. But usually, if you follow the steps in protein preparation wizard, the way we described here, you're more often than not, your system is good to go. You should not have any issues in running the calculation. So let's just wait for the job to finish. So it just started. It's going to finish in a while. I'll just close this panel. And once the job finishes, you should have a molecule 5 that loads up here in the entry list. So I'll just wait for that. There you go. The job finished, it minimized, and now I have the minimized structure. Now this minimized structure has a few things. So far what we did was we added hydrogens, and then we optimized the hydrogens, we got rid of all the waters, and then we minimized the whole structure to make sure that there are no steady clashes or anything like that. Okay. The next thing that you want to do is you want to build a system for simulations. So far, all we have done is we just prepare the protein. So the next step is to automatically, naturally build the whole system for simulations. So to do that, Schrodinger has a very simple panel, which is called System Builder. So to find the System Builder, you go to Task, which is here on the top right, and you go to Browse, and then you go to Desmond. You click on Desmond, and you have a few options that you can see here. You click on System Builder. That's the one that you need to build the system. So just click on System Builder, and you have a panel that opens up. And here you can you have different options here. You can set up a membrane if you have a membrane bound protein. So you just click on the setup membrane. You have a few options here. If time permits, I might look into this later, but this particular protein is not membrane bound, so I don't want to set up a membrane. All I want to do is I want to set up a solvent model. So there are different water models that are available here, SPC, TIP3P, TIP4P. For this exercise, I'm going to choose TIP3P. I'm just going to select on TIP3P, and now I have TIP3P selected. The next thing I want you have is you have boundary conditions. Now, if you're doing a simulation, you have to define boundary conditions. And that is basically, you define the shape of your box. You have different shapes here. You have orthorhombic, cubic, truncated octahedron. You have a few other shapes here. We're going to go with orthorhombic for this particular setup. And so let's just click on orthorhombic here, which was the default option. The next thing you want to do is, first click on Show Boundary Box. If you click on Show Boundary Box, keep an eye on the workspace. See what is happening in the workspace when you click on that. Right? Let me just drag this a bit to the left. I'll just click on this. Now you can see that a box formed around your protein. Now you can see that the box is not centered around the protein. So it's like it's to one side of the protein. So the protein is to one side of the box. It's not at the center. So to fix that, what you want to do is you want to go back to System Builder. And now I'm going to click on Minimize Volume and see what is happening to the structure when I click on Minimize Volume. You can see that the protein is now centered in the center of the box. So you can rotate it, you can see, and you can see that the protein is exactly in the center of the box. So it's essential for you to click on Minimize Volume. Okay. The next thing that you want to do is, maybe if you want to add some ions to the system, if there is a net charge on the system, you can go to the Ions tab here. So let's just click on the Ions tab here. And you have a few options here. We want to neutralize the system, so we can, by default, it calculates how many ions it's going to add to your system. But you can always recalculate it if you want it to be. And I'll click on Recalculate. And you can see that even after recalculate, I still get 5 chlorine ions here. So there's nothing changing here. And you can add salt if you want to add salt to your system. And this is dependent on if you're trying to make your simulation as close to experiment as possible. And if the experiment had salt in the system, then you want to add salt in your simulation as well. So I'll just go and add salt of 0.15 molar. It's a sodium chloride salt. And finally, you choose your force field. Again, OPLS3 is the most recent force field. So just choose OPLS3 as the force field. So just to recap, the things that we did so far was that in System Builder, we first identified the solvent that we want to use for our simulation. I chose T3P here, but you can choose anyone that you want to use. And then I chose the boundary box. Boundary conditions is orthorhombic, that's the box shape. And then I clicked on show boundary box, and we observed that the protein was not at the center of the box. And so to make sure that it's at the center of the box, we clicked on minimize volume. And it got the protein to the center of the box. Then we added ions and we added salt. And just click on run. So it's going to build the system. Right now, we don't see any water molecules, but once you click on run, it's going to add all of these things, all the water molecules and the ions in your system. So I just clicked on run. It's submitting the job. It's going to run the calculation. And we can monitor the job here by going to jobs and click on monitoring and check how the job is running. But so far, I'll just wait for it to finish. I don't want to do the monitor because I know it's going to run well because I have done this before for the system. So it's going to take around 1 minute, I guess, to build the system for this particular molecule. And let's just wait for it. Again, if you have any questions, keep posting the questions in the chat box and we'll get to them at the end of the lecture. Once the system builder is done, you're going to see a new molecule appear here. So I'm just waiting for it to appear here. It will be named as 6, entry number 6. There, it finished. It's incorporating the job that is completed. And you can just load this here by clicking on this here. And you can see that the system right now, you can see the protein here. You can see the ligand if you zoom in. And you can see all of these water molecules that we added right now. All of these are T3P water molecules. You can see the shape of the box. It is orthorhombic. And you can see that it is well built. It has the right shape. And so the next thing that you want to do after you build the system is you want to set up the simulation. So you go to task, right? And then you go to browse. And then you go to Desmond. And then you have molecular dynamics here. So you click on molecular dynamics. Now, if you want to do replicate exchange, you click on replicate exchange. If you want to click on do metadynamics, you click on metadynamics. If you want to do binding post metadynamics, you click on binding post metadynamics. If you want to do FEP plus, you do FEP plus. But we are going to do a simple MD simulation here. We'll just click on MD simulation here. So just click on that. And you have a panel that opens here. Now, first thing that you see in the panel is that you have the option of choosing the system. Which system are you going to use for the simulation? So you don't want to run the simulation on any of the molecules that are before. You want to run the simulation on a molecule that has water around it, and it would just minimize. So we're going to choose this one, right? And so I'm just going to click on load from workspace because that molecule is in our workspace. I'll just click on load, or you have different option like import from file. But since the molecule is already in my workspace, I'm just going to click on load here and observe what is going to happen after you click on load here. So system is not specified. And once you click on load, it says that 3LAU is a system. It's minimized. It contains 31,059 atoms, right? And the next thing that you want to do is you want to set up the simulation time. So a typical time would be, depending on what you're trying to study, it can range from a few picoseconds all the way to microseconds and sometimes to milliseconds. But for this particular demo, I'm going to just set it as 10 nanoseconds. So you can see that the time is 10 nanoseconds, and it's going to record your structures every 10 picoseconds, which means that you're going to have 1,000 frames because, if you're writing every 10 picoseconds, you're going to have 1,000 frames in your trajectory at the end. You also have the option of saving your energy, how often you want to save the energy. I'm also going to change this to 10, but this is just like numbers that I'm choosing here. You can try to modify it depending on what you're trying to study. A good thing to do is, you should always try to record your frames at least every 10 picoseconds, every 20 picoseconds, so that, even if you think that your motions are going to take longer than 10, 20 picoseconds, you can always exclude frames later. It's just good to record the trajectory with more number of frames right now than to not do that. Okay. So this is just the simulation parameters that we chose right now. The total time for the simulation, how often are you going to save your frames so that you can look at the trajectory later, and how often are you going to save the energy here. The next thing that you want to do is you want to choose the ensemble class. You have different ensembles here. You have NVE, NVT, NPT, which is NVT is normal volume and temperature. NPT is normal pressure and temperature. NPAT is normal pressure, area, and temperature. And NP gamma T is normal pressure, surface tension, and temperature. The last two options are ones which you're going to choose when you're trying to do a simulation that has membrane in it. But if you do not have membrane, as is the case for this protein, you can choose NVT or NPT. The default is NPT. Let's just go with the default here. And you can see that the temperature for the simulation is around 300 Kelvin, and the pressure is 1 atmosphere, 1 bar here. It's atmospheric pressure. So you have the option of relaxing the model system before simulation. So right now we added water, but this water will still have, like, it's not properly minimized and packed. So you want to relax the system. You want to heat it up to the target temperature. So you want to do those things. And for that, you just select this option here. It's going to make sure that it's slowly going to heat up the system to the target temperature and the target pressure. It's going to relax the system. It's going to get rid of state clashes. It's going to minimize and equilibrate the system during this whole step. All of this is done in the background. All you have to do is just click on this step. It's going to automatically generate the files that are required for doing this calculation. It's going to run the calculation for you. And after that, you're going to do your production run for the simulation. You also have a few advanced options here. So you can go to advanced option, and this advanced option has a panel where you can choose the timestamp that you want to use for the simulation. The default options work well. I just want to point out the options that you have here. So here, the 2 femtosecond is the timestamp that you have for bonded interactions. And you can choose the ensemble here. So for the ensemble, we chose the NPT ensemble. So NPT is normal pressure and temperature. So you need to have a way to make sure that the temperature stays at 300 Kelvin. So to do that, you have a thermostat. The thermostat that you have different thermostats here. You have Nosse-Hoover, you have Langevin, you have DPD, and you have none. And we're going to choose the default option, which is Nosse-Hoover, and we're going to use that. You have a few options here for relaxation time. Just use the default options, so you are good to go. And for the barostat also, you have 2 different barostats here. You have Martina, Tobias, Klein barostat, and you also have the Langevin barostat. You can choose either one of them. We'll just choose the default one. So let me just choose this one. And you can go to interactions here. These are for long-range interactions, such as electrostatic interactions. What cutoff value do you want to use? You have cutoff that are different here: cutoff, potential tapering, forced tapering, and shift. We're just going to use the default value of cutoff here. You can change the cutoff radius from 9 to 10 angstrom or 11 angstrom, or you should always have it at least 8 angstrom. It's recommended to have at least 8 angstrom. But 9 is a good number. Go with the default values. And if you think that, if you want to restrain some of the atoms in your system, you only want to simulate a local region of the protein and not the whole global region, then you can add restraints here. You can also add center of mass restraints. You can do a lot of different restraints here. You just go to click on add, select the atoms that you want to restrain, and you can just add them here, and it's going to restrain those things, restrain those atoms. The next option you have is output. You can choose the job name for your output files. You can choose if you want to record the velocities. You can also choose a checkpoint file. These checkpoint files are like restart files where, let's say that you are running a simulation, your simulation crashes in between. And if you want to start from where it crashed, you can just use this checkpoint file to start from where it crashed. For example, you had a power cut, your whole cluster got shut down, and you can't run the calculation anymore. You can always choose this checkpoint file as a starting point. You can run the calculation after that. So it's going to record the checkpoint files every 240 picoseconds. You can change this value to whatever you want it to be. We'll just leave the default options that are available here. And the last thing you have is miscellaneous options, which are like, randomized velocities. For example, whenever you do a calculation, if you want to do like multiple independent runs, then you want to randomize the velocity so that you have different starting points for your simulation. Even though you have all the atoms the same, everything is the same, if you have different random velocities for each atom, you're going to have a different trajectory path for your simulation. And people often do this because irrespective of what your starting velocity is, you should get the same answer. And so even though you start from a different velocity, different starting velocities, by the end of some 50 nanoseconds or 100 nanoseconds, your simulation tends to give the same answer, which indicates that your simulation is well converged, and you can use that to give error estimates on your simulation. So just to recap this panel, so what we did was we went to advanced options. We have these are different options that are there. The time step, the ensemble, the thermostats and baristors that you can choose, the long range interactions, the Coulombic interactions that you can choose here. If you want to add restraints, you can add restraints here. Output files, the restart files, the checkpoint files that you can use for restarting calculations, and randomizing velocities, or if you want to do other things here. Okay. So I don't want to change any of these options from the default. I'll just click on cancel, and I have the default options here. And if you want to, because we have protein ligand complex, we can automatically run a simulation, run the analysis on the simulation finishes. We just select this option. It's going to choose the protein automatically. It's going to choose the ligand automatically. Or you can also define the atoms that define the ligand, or you can define the atoms that are part of the protein. You can do both of them, but I'm just going to leave them as auto here. If you don't click this option, you can always do the analysis later. And because I'm going to show you how to do the analysis later, I'm just not going to select this option here. I'll just deselect this. And just to recap this whole panel, we just loaded the molecule. We set the simulation time to 10 nanoseconds. And we are recording the structures every 10 picoseconds. We chose the ensemble. We chose the temperature. We chose the pressure. We want to relax the system before we do the actual simulation. And then we looked at some of the advanced options that we have. And we chose not to do the analysis right now. We're going to do it later. And all you have to do is after that, you just click on run. If you have a Linux machine with the GPU card on it, this is going to automatically run the job for you on the GPU that you have. So I'm using a Windows machine for this demo session, so I'm not going to run the simulation right now. But if you have Linux, you can just directly do it. The other option that you have is, let's say you have a Windows machine for using the Maestro interface and you want to choose Linux only for running the calculation. In that case, you can just go to this option here. You can see the drop-down menu here. Just choose this. You can click on write, and that's going to write all the files that are necessary for this calculation. You can copy the files to your Linux cluster. You can run the calculation from your Linux cluster just by doing this. So just to show you again, you just go here and click on write. It's going to write all the files that are necessary for the simulation. Now, because I only have Windows here, I'm not going to run the calculation. I did the simulation beforehand already, so I'm just going to load the simulation that I did before. Okay. So I'll just close this here. And what I'm going to do next is I'm going to import a structure, right? So I already did the simulation beforehand. I'm just going to load the simulation that I did before. So I'm going to go to import structures, and I'm going to go to the place where I have the files. So when you do the calculation, you're going to run the simulation, you're going to have a lot of different files. You can see that there are so many different files here. All of these are from a single simulation. The file that you're looking for is Desmond MD job out.cms. Okay, Desmond MD job out.cms. CMS is similar to a topology file in other softwares. It just tells you how the atoms are linked to each other. So I'm just going to load that. And when you load a simulation file here, you can see that it has the option that I have a molecule that is loaded here, which is entry number 7. And next to that, if you look at it here, you see a T symbol here. This T indicates that you have a trajectory that is part of this file. So you just right-click this. So if you right-click on this one, you have the option of load trajectory. So I'm just going to click on load trajectory. And you can see that the trajectory loaded here. And you can see that the frames are there from 1 to 1043. Now, this was a simulation that I did before for 5 nanoseconds. I'm just running the calculation for that. This one had different parameters than what I showed you. So that's the reason why I have 1043 frames in 5 nanoseconds. Now you can look at the box here. This is similar to what you had before for the 3LU minimized. It's just like it's better equilibrated, and the simulation is run. So to look at the trajectory, all you have to do is you can see the frames here. You have different options here. You just come here and click on play. And you can see that the simulation is playing here. You have this water box, all the water molecules are moving. You can see the protein is also moving here. The ligand is over here. And it's not really clear for you to observe any of these things. It's like too complicated for you to see. And so one thing that you can do is you can change the playback settings. But before I do that, so you have a few playback settings here. You can choose the playback settings. You have different options here. You have the speed option. So do you want to look at every frame of the trajectory, or do you want to skip some frames? So if you want to skip some frames, change this step to, let's say, 5. So I want to look at 1 in every 5 frames. I don't want to look at every frame of the trajectory. And you can choose that, and you can go and click on play. It's not really smooth as it was before. You can see some jumps that are observed here. So you can also do some smoothing. So you can click on smoothing. You can change this. I'll just choose 5 for this also. And you can click on play. It's a slightly slower, but with all the water molecules, it's difficult to identify what is happening here. So let me get rid of all the water molecules. I'm going to go to preset. I'm going to double click on this. It's going to zoom into my ligand and the protein. Now I can see the preset. I'm going to click on play right now. You can see that for this simulation, the ligand is over here. The protein is over here. You can see the interaction that the ligand is forming with the protein. You should also be able to see a few water molecules that are here. The water molecules are trying to interact with the ligand, and then they are diffusing back to the bulk solvent. So you can look at all of these things here. And if you also want to do further modifications, you can change the view of your trajectory here that you're visualizing. You can go to advanced options. You can choose the display only atoms matching particular strings. So you can go here, you can click on atoms that match a particular atom definition. And so display only, you can go here, click on the plus button here, and you have a panel that opens up, which opened. So you have a panel that opens up here. You can choose the atoms that you want to view. I'm going to go to residue here. I'm going to click on residue type, and I have different types that are visible here. I want to center my view around the ligand. So I'm just going to go to OFI, which is my ligand. You have chlorine ions. You have all the amino acid residues here. You have chlorine ions that you added. You also have SPC for the simulation, which I use as a water molecule, even though I use tip3 when I was doing the calculation. So I'll choose OFI here, click on add, and I click on OK. Now my whole view is going to be focused on the ligand only. I'll just click on OK here, click on play, and I can just see the ligand here. I don't see any of the protein is still visible, but it's mostly focused on the ligand here. So you can change this playback settings here. And if you also want to save a snapshot of your trajectory, you can go to workspace, save image as, and you can save the image that you want to save. Now, looking at this here, right, we are trying to look at the trajectory here. And it forms different interactions. You have all of these water molecules, you have all of these amino acids. You can turn on the interactions here. You can see that it forms a few hydrogen bonds. You have a few other interactions here. And so looking at this in a trajectory format like this, it's very cumbersome to look at. And you don't know what exactly is happening. Water molecules are coming and going. The protein is changing. The ligand is forming interactions with the protein and it's breaking. It's very difficult for you to get an understanding as what is happening. And so is there a better tool for you to analyze this simulation? And to do that, Schrodinger has a very good tool called the simulation interaction diagram, as mentioned by Shelvia in the introduction. So we want to analyze the simulation and we want to get really pretty pictures and graphs as what is happening in the simulation. So to do that, I'll just go to task, go to browse, go to Desmond, and you have the simulation interaction diagram here. Okay, browse, Desmond, and then simulation interaction diagram. So if you open the simulation interaction diagram, you have a panel that opens up. The first thing that you have is you have the option of load. Okay, you can click on load, and when you click on load, the thing that you want to load is again the same file that we loaded into the workspace here, which is md job1 out.cms. Okay, and you click on open, and you click on, and once you click on open, it's going to show you a panel. It's going to try to import the file. It's trying to do the society analysis setup. And if you haven't done analysis before, you can choose the analysis here. You can choose the protein atoms here by defining an atom selection string list. You can also do the same for ligand, but if you only have one protein and one ligand, the software is good enough to identify what the protein is and what the ligand is, so you don't have to do that. You can choose the reference structure. You can set it to frame 0 of your simulation, or you can load a PDB file. Like, for example, you can load your experimental structure as a reference file. It's going to do all the analysis based on the reference structure that you have. You can choose different analysis that you want to run. You can just select all. So it's going to do all of this analysis. You just click on run, and it's going to do the analysis for you for the whole simulation. I don't want to do this right now because it takes around 5 minutes to do the analysis. So I already did the calculation. I already did the analysis for this particular simulation. So I'm going to cancel this. I'm going to go back to load. And if you do the simulation interaction diagram, and if you load the .cms and if you run the calculation, the file that you're going to get as output has an extension of .eaf. EAF stands for event analysis file. So since I already did the calculation, since I already did the analysis, already have this file loaded here. I'm just going to click on select this file. Okay, click on open. This will have all the analysis that has been done before. It's going to load all the data from the analysis, and you can, let's just wait for it to load. It should take like probably 5 to 10 seconds. And here you can see that the whole simulation has been analyzed, and you have the output for the simulation here. Okay, so you have different panels here at the top. Each of these correspond to different analysis. We are going to go through each one of them step by step. So this is the first panel, which is protein ligand RMSD. So RMSD is the root mean square deviation. So it tells you how much your ligand and the protein are moving with respect to your reference structure. And for the reference structure, we chose the first structure of the simulation as a reference. So you can see for this graph, on the x-axis, you have the time in nanoseconds. So we have from 0 to 5 nanoseconds because that's how long this particular simulation was run for. On the y-axis, you have the protein RMSD here on the left side, and you have the ligand RMSD here on the right side. Okay, both of them have the same axis here, but in some cases, you might have different axes depending on what the range of the values are. And you can see that this particular ligand RMSD is shown in maroon color. And so this indicates that the maroon color line that you see here corresponds to the ligand RMSD. And the blue color line that you see here corresponds to the protein RMSD. And so what are you looking for in RMSD simulation in this particular graph? What you want to see for a stable simulation is if you're trying to study protein ligand interactions, the ligand should not unbind to the protein. If it should stay in the binding pocket. And if it is staying in the binding pocket, then you have a very low RMSD for the ligand. So you can see that the RMSD of the ligand here is less than 2 angstrom for the entirety of the simulation, which indicates that the ligand is staying in the binding pocket. It's also interacting with the protein, which we'll find out later when you look at all of these particular panels here. And if you look at the protein RMSD too, the protein RMSD, even though it fluctuates more than the ligand RMSD, it's still stable around 2.5 to 3 angstrom. It's not like going beyond 3 angstrom. So the protein is also stable in the simulation, and the ligand is also interacting with the protein. So this protein ligand RMSD just shows you that the ligand is stable in the binding pocket, and that the protein is also like relatively stable compared to the ligand. So it's not falling apart. So this is one analysis that you can do when you do your simulation for a protein ligand complex. Here you have the RMSD for C alpha. You can also see the RMSD for backbone. You can see the RMSD for only the side chains. You can see the RMSD for only the heavy atoms. All of these options are available. You just choose these options here. You can align the RMSD on protein, or you can align the RMSD on ligand. You're going to see that if you align the RMSD on the ligand, then the ligand RMSD which you're seeing here in pink, the ligand is mostly stable at around 0.5 angstrom with respect to starting structure. So you can just click on all these options. You can see what exactly you see here. So the next panel that we're going to look at is secondary structure for the protein. So this one has two different graphs. I'll go through each one in one by one. So the first graph that you see here is on the x-axis, you have the residue index for the protein. So this protein has around 250 amino acids, and you have this particular that is shown on the x-axis here. On the y-axis, it tells you the percentage secondary structure for each of the residues that are there. So the color indicates that blue is beta strand, orange is alpha helix, and white it just indicate loop regions. So if you see this particular graph here, you see that you have beta strands here, and you have breaks in between, which are loop regions, and you have the alpha helices here, you have breaks in between. So like which are also like loop regions here. And you can see that for all of these residues, the secondary structure content, if it is a beta sheet or if it is alpha helix, it's at least 75% for most of them except for this one. This indicates that the protein is stable throughout the simulation. There's nothing fancy happening in the protein. The alpha helices are remaining as alpha helices. The beta sheets strands are remaining as beta strands. And if you also go down here, you can see that this graph is changed. So here you have the residue index on the y-axis instead of the x-axis as is in this graph here, and you have time on the x-axis here. And you can see for each residue how long, like if it is in alpha helix or if it's beta strand, you can see what is happening to each of the residues here. If it's alpha helix, it stays as alpha helix for most of the simulation. If it is beta strand, it stays as a beta strand for most of the simulation. And so you can look at this particular graph here just to understand what is happening to the protein during the course of the simulation. The next thing that you can look at is protein RMSF. So the RMSF, which is different from the RMSD, the RMSD tells you how the overall protein is changing with respect to the reference structure. The RMSF tells you how long each residue is changing with respect to its reference position, the initial position. So instead of having time on the x-axis, you have the residue number on the x-axis. So you have 0 to 250, and on the y-axis you have RMSF. RMSF is root mean square fluctuation. Deviation is how much it moves from the starting position, and fluctuation is how much it fluctuates around the starting position. So you can see that for this particular residues, you have some of them have a high fluctuation, and some of them have a low fluctuation. And so overall, most of the fluctuations are less than 1 angstrom, which indicates that the residues are stable. You can also click on show the ligand contacts. So it's going to show you these green lines here, ligand. And you can see that for most of the residues that are interacting with the ligand, the fluctuations are very less, which indicates that the interactions are quite stable during the course of your simulation. So you can see this, it's very convenient to see, like, are the residues that are interacting with the ligand stable, which is indicated by low RMSF here. And you can see that for all the residues that are interacting with the ligand, the green lines, these ones have a really low fluctuation around 0.5 angstrom most of the time. The next thing you can look at is ligand RMSF. So similar to protein RMSF, ligand RMSF tells you how much the ligand atoms are moving during the course of simulation. So instead of having the residues of the protein, you have the atom numbers of the ligand. So you have from 1 to 22 atoms. So this ligand has 22 atoms. You can see the RMSF. This is aligned on the protein. You can click on align on the ligand. You can see that the RMSF decreases to 0.2 angstrom or something like that. And so you can see that if you look at the pink line here, the ligand is mostly stable, and you can see that some of these atoms at the end are fluctuating a lot. So you can use this, and you also have a ligand diagram here at the present here. You can see the atom numbers that are moving a lot, and based on that, you can try to modify this functional group in the ligand to make a stable interaction. So you can see that these particular atoms are fluctuating a lot, which means that the interaction is not that stable for these atoms. You can modify the ligand slightly to make sure that these atoms are modified, which can result in a more stable interaction with your protein. So this is convenient to see what exactly is happening to the ligand while the simulation is going on. And you also have other tabs that are available here. We'll just go to the next one here, which is protein ligand contacts. So far what we have done is we looked at the individual protein ligand RMSDs. We have looked at how the protein structure looks like. We have looked at how the protein RMSF looks like. We have looked at how the ligand RMSF looks like. And the next thing is we want to look at the interactions between the protein and the ligand, which are happening. So far, all we know is that the protein is stable, the ligand is stable, and maybe they're forming a stable interaction between each other. So the next thing that you want to do is you want to look at the protein ligand contacts. So for protein ligand contacts, this is the panel that I just clicked on here, and you have two different graphs here. We'll take them step by step. So the first graph that you look at here on the top here, you have the residues on the x-axis. In the previous graphs, you had all the residues from 0 to 250, but here you only have the residues that are interacting with the ligand. You don't have all the residues here. And on the y-axis, you have the interaction fraction here. And if you look at it here, for every residue, you have different bar graphs here. And you have, for each bar graph, you have different colors. And these colors indicate the type of interaction that the ligand is forming. So green indicates it's a hydrogen bond interaction. Red, which is not present here, indicates ionic interaction. So this particular ligand is not forming any ionic interactions with your protein. So you don't see any of the red color here in this graph. And if you look at this violet one, that's hydrophobic interactions. And if you look at the blue ones, they are forming water bridges here. And so for every residue, it's going to give you a really pretty graph that shows you all the interactions that your ligand is forming with your protein. And so if you look at this particular graph here, you can see that alanine 213 forms a hydrogen bond interaction with your ligand. It's very stable. It's present for a long time. You have a high fraction of this. If you also look at glutamate 211, that also forms a hydrogen bond interaction with your ligand. You can look at lysine 162. It forms a hydrogen bond interaction. It also forms, for majority of the time, it forms a hydrophobic interaction. For some times, it forms water-mediated interactions. So for every amino acid on the protein which forms interaction with the ligand, you can look at the interaction that is being formed, what type of interaction that is being formed in a very clear picture here. And if you go to the bottom graph is just the same graph that is inverted. So instead of having the amino acids on the x-axis, you have the amino acids on the y-axis here. And you have time on the x-axis here. And you have colors. So you have colors that are ranging from white to dark red. And so the color indicates the number of contacts each of these residues are forming with the ligand. So if you look at this particular graph here, white indicates that 0 contacts are being formed. 1 indicates that, slightly orange color, like light orange is like 1 contact with the ligand. A darker orange is 2 contacts with the ligand. Even darker orange is 3 contacts with the ligand. And red is like greater than 4 contacts with the ligand. So if you look at these residues here, we observe that alanine 213 has a hydrogen bond interaction with your ligand. And if you look at this, alanine 213 here also has a large number of contacts with your ligand. Now, these contacts are mostly in this range, which is 2 number of contacts with the ligand. And sometimes it also forms like just only 1 contact because the amino acid the protein is changing during the simulation. So contacts form and break. But through the simulation, this contact is mostly stable. You can also see this one here, which is glutamate 211. It forms 1 contact with your ligand. It's mostly stable for the simulation, except for this region here, which is like, the contact is broken, but it forms again instantaneously. However, if you look at glutamate 260, this one has no contacts with your ligands. It's mostly white, 0 contacts. And you can also see some of them like leucine 210, which forms a contact, which breaks the contact. It's like forming and breaking. So you can see all the contacts that are forming here. So to summarize this particular panel here, you can see the interactions that are forming with the between the ligand and the receptor, and you can see what type of interaction is forming between the ligand and the receptor. You can also see the same from a ligand point of view. So if you have looked at this ligand interaction diagram that we looked at during docking analysis, it's the same image here where you have the ligand here and you have the protein amino acids that are forming the interaction with the ligand here. And you can see the type of interaction that is forming, if it's a hydrogen bond donor or if it's hydrogen bond acceptor. So you can see all of those things, which is similar to what you saw for docking. But in addition to that, the information that you also get in here is how long is the interaction stable for. So for example, if you look at this particular interaction here, this is stable for 99% of the simulation. So this is a very stable interaction. It never breaks. And if you also look at this one here, it forms the interaction for 94% of the simulation time. So out of 5 nanoseconds, this interaction is stable for almost 4.5 to 4.7 nanoseconds of the simulation. This one is stable for all the 5 nanoseconds, almost all the 5 nanoseconds. So this tells you, like, which part of the ligand is forming stable interaction with my protein. And for example, if you take a look at this one has only 57% of the, is present for only 57% of the simulation. So because of that, if you want to make your interaction between the ligand and the protein more stable, this tells you that you can try to modify this particular atom on the ligand, this particular group on the ligand, to make sure that you have a more stable interaction with your protein. So this is a very convenient way to analyze your whole simulation, which tells you like which interactions are stable, which ones are not stable. And based on it, you can try to further refine your ligand to make sure that you get a much more stable interaction between protein and the ligand. And you also have other panels here, which is ligand torsions and ligand properties. You can look at all of these things. What is the surface area for your ligand? What is the polar surface area? What is the molecular surface area? The radius of gyration, the RMSD. So you can do all of these things. I'm not going to details in all of the details of these plots. So just to summarize this whole panel, you have the protein ligand RMSD, which tells you if the ligand and the protein are stable. The same thing with protein SSE. The same thing with protein RMSF. With the ligand RMSF2, you can find out which atoms in the ligand are moving less and which ones are moving more. And you have the protein ligand contacts here, where you can see which type of interaction being formed between the ligand and the protein. You can also look at it from a ligand point of view with the simulation, with the ligand interaction diagram. You can see how long each interaction is stable for. And you can look at all of these plots in a very convenient way. You can just save them. You can use these plots for your publication directly without any modifications. So, you can also like generate a report. So you click on generate report. You can generate a PDF report. You can generate a PDF report with all the plots and the data, and it's going to generate all of these things. It's going to write all of these plots and the data to your hard disk. You can look at this data later. You can post process them if you want to, and so you can just click on OK. It's going to save all of these images in a PDF file. It's also going to save all the raw data. It's also going to save all the plots in your folder. So let's just wait for it to save it. I think it's done. I'm just going to close this panel here. Let me just wait for it to respond. Okay, I don't know why that is stuck, but let me show you my working directory where I saved the files. So I went to tutorials, and then I saved this as my MD simulations. That's there. So I just click on open that. And then I saved all the data that I got from simulation interaction diagram to here. So I just click on data one. Here you can see all the images that you have saved before. So you can just load them here. You can just go one by one. You have all the graphs that are visible here if you just want to use them for your publication. Or you can also go and look at the raw data where you have all the data.dat files for all your calculations. You can just look at these files, open them. If you want to plot them in a different way using your plotting software, you can do that as well. Or you can also go and open the PDF file that we saved. So if you just click on this one, A PDF file opens with all the data for your simulation. So there's the report from the simulation interaction diagram. You can just go through this. It shows you all the plots here. It also gives you explanation as to what exactly is being calculated here. So how is the RMSD calculated? And what does RMSF stand for? And you have all of these graphs that you looked at before. All of these things are produced in a report. You can look at the ligand RMSF. You can also look at the protein ligand contacts. It tells you the description of all the things that is being calculated. What is the criteria for calculating all of these things? Hydrogen bonds, hydrophobic contacts, ionic interactions, water bridges. We also have a report for the protein ligand contacts where we looked at this graph before. And you also have the ligand interaction diagram. And you can also look at the torsion profiles for the ligand. You can also look at the ligand properties. So all of these things are present in one single place and tells you how each of these properties are calculated. So just to summarize what we did so far for this whole session, we loaded a protein pre-warmed. We optimized the hydrogen bond network for your protein ligand complex. We removed any waters that were present. We minimized the whole complex. Then we set up the system using system builder, where we chose the water molecules that we want to use. We defined the box shape. We added ions. We added salt. We chose the force field. And then after that, we set up the simulation parameters. We chose NPT ensemble. We chose a thermostat, barostat. We looked at different options that you can choose. We relaxed the system before we did the production run. We ran the simulation, which we didn't do for this particular case, but you're going to do it on your Linux machines. And then after we looked at the analysis for the simulation, we looked at the trajectory first in the workspace. And then after that, we also looked at the different playback settings here. And then we also looked at the simulation interaction diagram, where we looked at all the analysis that you can do for your simulation, which it automatically determines your protein. It automatically identifies your ligand. It's going to do the whole analysis for you. It's going to give you RMSD plots, RMSF plots. It's also going to tell you about the interactions that the protein is forming with the ligand. If it's hydrogen bond interaction, if it's hydrophobic interaction, if it's water mediated interactions. It's going to do all of those things for you automatically. You can just look at them. You can write the output to an Excel sheet to your hard drive. You can use those files to plot it later using the plotting software of your choice, or you can just use the images directly from the hard drive that you saved to. So with that, I would conclude this session. I haven't gone through how to build a membrane, but if anyone is interested, we can also show it later. But it's very simple to do it. There are tutorials available on the website. You can just go to help at Schrodinger, and you can just look at the options that you have over there. And you can easily see how to build a membrane also. And with that, I'll be happy to take any questions that you have. Thank you all for joining in. And yeah, I'll take the questions next. Thank you.
Thanks, Kaushik. I've been reminding to tell you that could you please show how to merge a protein and ligand from docking vessel in order to generate a complex that we can take for the Desmond system builder?
Sure. Yeah, I can do that. Let me just share my screen again. So, okay. So let's do one thing. Okay. So I have this particular protein here. Now I think I have a protein ligand complex. Let me just load that itself instead of trying to do this. I don't know why my maestro is not responding. Just give me a second. Okay, I need to close this. All right, good. File, I'm going to import a structure from that I did before. I'm going to go to here. Nope, not that one. Talking MD workshop files. Okay, let's do this. I'll just use this. Okay, I'm going to split this into ligands and water. So now I have a protein that is just protein. Turn off all the labels, and I'll have a ligand that is just ligand. Okay. Now, if you're doing docking with your different ligands and if your protein, and if you want to just combine them into complex, now if you do docking, you're going to have a post viewer setup. And so if you have a post viewer setup, then so you know where the ligand interacts with the protein, and you know that the ligand and the protein are two different files. So all you're going to have is the same particular setup. You're going to have a file that has a ligand, you're going to have a file that has a protein. And all you have to do is just select the two of them and click on merge. There should be a merge somewhere. Um, okay, group probably. Um, let me try that. Actually, let me just. Do you have any other questions while I figure this out?
Yeah, we've received a couple of questions.
Sure.
So the first question is, uh, what are like which force field are better, and what is the difference between OPLS 2005 and OPLS 3?
So OPLS 3E is the most recent force field, which was published in 2015, and OPLS 2005 was published in 2005. And because 3E is the most recent one, it is better to use it because it covers 95% of the chemical space. It covers the parameters for all your proteins, all the ligands, most of the ligands, uh, nucleic acids. It covers parameters for a wide range of compounds. Yeah.
Right. So the next question is, as it is said that we have to take extra precautions while using cryo-EM structure. So what are the extra steps that we need to do while protein preparation of such structures?
So if you are using a cryo-EM structure, so you follow the same set of precautions, but the thing that you would have an issue with cryo-EM structures is that the resolution is not that good for cryo-EM structures. Most of the structures will have a resolution of 3 to 4 angstrom at least, and so you're going to have missing side chains or missing loops. So you're going to follow the same set of precautions for that. We do have a tool that is in the process right now to import and process cryo-EM structures, but write an email to me and I can go into details of it later. But we actually have a tool to do that. But other than that, you just follow the basic steps of protein preparation wizard, and that should fix it. Yeah.
Right. So the next question is, why did we delete water beyond 0 angstrom? Default is 5. Why did you make it 0?
So I just wanted to delete all the waters for this particular set of for this system, and so you can. So if you choose 5 angstrom, it's going to keep all the waters that are within 5 angstrom of your ligand. It's a choice that I made. It depends on the system that you have. You can keep it. The reason why you want to keep it is if you think that the water is important for the interaction between the ligand and the protein, then you can keep it. But I just chose to delete it for this one, so I just deleted it. There is no other reason than that.
Right. So the next question, I think you already went over this. Are you doing all these things in a Linux system?
No, I did all of this setup in Windows machine, but the simulation itself has to be done on Linux. The analysis can be done on Windows. The setup can be done on Windows. Even the MD simulation setup panel can also be done on Windows, but the actual simulation has to be done on a GPU on Linux.
Right. So the next question is, suppose you want to keep the solvent as ethanol. You showed there were only a few solvents that were available. Can we do this in disordered system in MS Suite? How can this be done?
Can you repeat the question, please?
Can we use solvent as ethanol? That's the main question.
Yes, you can do it. So the options that you have in the panel are the default ones that we have, but you can always modify your system. We have command and options for that, and you can set up your system with anything that you want to use.
Right. So the next question is, how can we validate?
Sorry, Shalvi and Kaushik.
Yeah.
So there
Okay.
is a disorder system builder in our MS suite in Schrodinger. So you can use that for building up any solvents. So through GUI, you can set up that.
Right. So the next question is, how can we validate the molecular dynamics results?
Yes, so I have shown you so many plots that are there for protein ligand RMSD, RMSF, and the interaction between the protein and the ligand. And all of those things can be used to validate your simulation. And so you have to make sure that your simulation is converged. By that, I mean that the values do not change if you run it for a longer time. So for example, you run a simulation for like 15 nanoseconds, let's say, and you get some answer for that. And let's say you run it for another 15 nanoseconds. Your answer should not change drastically. It should still be same. And that means that your simulation is good enough for you to validate it. But of course, you have to look at all the graphs that I have showed you so far, and that's how you validate it.
Thank you. So the next question is, when I try to fill the missing loops, it always results in the failure of job. What can be the possible reason, and how can I correct the problem?
Um, um, we don't know exactly what happened with your particular calculation. Do you have prime module with you? If you have prime, then it should be able to build the loop. But if it failed, then look at the log file and see why exactly it is failing and let us know why it is failing. And based on that, we can help you out. But I can't really tell you why it might fail off the cuff.
Right. If you have any questions, sorry. Yes.
Yeah, just add on to Kaushik comment. Exactly what Kaushik mentioned is right. So it could be in particular to whatever protein you are working on. Rather, there could be one more reason. If more than 4 residues continuously are missing, then protein preparation wizard will not fill it up. So up to 4 residues only it will fill it up. So anything more than 4 residue continuously, if it is missing, then it is always advised you should go for homology modeling rather generating model through protein preparation wizard. So there could be more than 4 residues continuously missing in the protein. Probably that is the reason it did not build it.
Thanks, Pritesh.
Right, so you can also join us during our office hours, which are Thursday from 4:30 to 5:30 p.m. So if you have any questions, that is the time dedicated for those. So if you're facing something, some issues while doing something, that is the best way to actually interact with us one-on-one. You can share your screen, we can look at the issue and solve it. So that is one of the ways you can ask us these sort of questions, like why is this happening, why the jobs are failing. And obviously you can write to us at ddcourse@schrodinger.com as well. Right, so the next question is, on what factors do the simulation time period depend?
So it depends on what you're trying to study. I think I showed you if you look at the theory one, let me just share this slide with you. So I hope you can look at the slide here. And so if you look at this slide, different motions of your biomolecule happen on different time scales. And this is what determines how long you have to run the calculation for. So if you're just trying to study cycling conformations, then you can run it from picoseconds to nanoseconds. But if you actually want to study the interaction of your protein with your ligand, if the interaction is stable or not, then if 50 nanoseconds to 100 nanoseconds is good enough. But if you want to study like ligand binding and unbinding, which is the ligand has to come from the bulk solvent, interact with your protein in the binding pocket, and go back to the bulk solvent, then those interactions happen on the order of microseconds to milliseconds, and that's what determines how long you have done the simulation for. So, and how do you choose the parameters for saving the files? It's always recommended to save your trajectory snapshots every 10, 20 picoseconds so that you can post-process them, see what exactly is happening in your simulation.
Right. Thank you for the answer. So the next question is, on what basis do we adjust the time, energy, and other parameters in MD?
So I just answered this. It again depends on what you're trying to study. But the time that you want to say the structures for 10 to 20 picoseconds is recommended. But you can also do it, you know, it depends on what you're trying to study. So if you have a loop motion or if you have like binding and unbinding, which is going to take you like microseconds to milliseconds, then you can save your structures every 100 picoseconds. Or if you're studying suction rotamers, then you can save every 1 picosecond. So it depends on what you're trying to study. The energy parameters, you can save it every 10 picoseconds because energy files are not that big. So there's nothing wrong in saving them more frequently. The only disadvantage to saving your files more frequently for trajectory snapshots is that the file is going to be very huge on disk. So that's the only reason why you might want to restrict saving them more often. But 10 picoseconds, 20 picoseconds is a good choice for most studies. The same for energy, saving energy as well.
So the next question is, so again, there is a question about the job failing. What could be the possible reason for MD simulation to crash in step 2?
So I don't know exactly what step 2 refers to here. If it is the equilibration protocol, which has 6 or 7 steps, so we're spelling step 2 of that. It could be because you might have some, the minimization not complete, but I don't know what step 2 is here, so I can't really explain that. Yeah.
Okay. So the next question is, can we hide waters during MD playback to observe only the protein?
Yes, you can do that. So I just showed you how to select your view selection area using the playback settings. And if you go there, you can just choose not water. So you can easily do that. So let me just show you with a brief example here. So where is my simulation? Okay, and then not that. 3 LU minimized, 3 LU this, 3 LU this, and that's my trajectory. Okay, go to playback settings here, go to advanced here. You can look at just the ligand, or you can go to here and change what you want it to be. So we just go to select, go to residue type here, SPC. I'm going to add that. And let me just delete that. And I'm going to invert this. So it's going to show you everything that is not SPC. So that way you can just look at everything that is not SPC. You can then play your trajectory here. You can just look at everything that is not your water. So you just go to playback settings here. You go to advanced. You can choose the ones that you want to choose and just click on play. Yeah. So just select the atoms that you want to view. Yeah.
So the next question is, what is the significance of leg fit to prot, as in protein, RMSD plot maxima point?
Um, can you repeat the question again, please? I just missed it.
Okay, so is there any significance of the ligand fit to protein RMSD plot maxima point?
Yes. So there are two ways you can align your molecule. So the first one is you can align your molecule on your whole protein, or you can align your molecule on your ligand. Okay. So if you align it to your protein, you want to align it to your protein because what you're trying to study is how the ligand interacts with your protein binding pocket. You don't really care what exactly happens to the ligand when it is fit to the ligand. So if you say that, let's say that your ligand is in the bulk solvent, and it's trying to diffuse to the binding site. Then you're going to have a high RMSD if you fit to the ligand. But if if you're trying to study your binding pocket, then it's always recommended to fit it to your oral protein, because even if the protein changes, you can still study it with respect to the protein, because the interaction that you're trying to look for is between the protein and the ligand. So try to fit it on protein, the ligand on fit to protein, and use that. I don't think I made any sense with that, but there is no significance on it. It's just the way people do it usually. It's just more clearer.
Right. So the next question is, what is the role of SPC/OFI in different residues?
So SPC was the water molecule that I used for this particular simulation. Just to clarify, when I was setting up the calculation, I used TIP3P, but that was just to show you how you can choose different water models. But the simulation target that I loaded used SPC water. And OFI is my ligand name. So the residue name is OFI for my ligand. And there is no role for them. It's just that my simulation box has SPC and it also has OFI. SPC water and OFI is my ligand.
So the next question is, can we get the raw data of the graphs in Excel in order to replot some of the graphs in other graphing solutions such as GraphPad?
Yeah, I showed you how to do that. You open the simulation interaction diagram and then you click on generate report. It's going to save all the data on your drive, and you can look at the data and you can use any plotting software of your choice and plot it.
Okay, so the next question is, I think it means the question is how to work with different solvent models for molecules such as TIP3P or SPC, etc.
I don't know what the question means. If it is about how to choose a water molecule that you want to use, you can use any one of them. Most often, they all are similar to each other. There are a few differences that are there, but it again depends on what exactly you're trying to study. But any of them should give you a decent answer.
Okay, so next question is, how do I change the dummy host, GPU host to set a valid CPU or GPU host? How can we configure it?
I think you have a dummy GPU if you're using a Windows machine, and if you use Linux, if you have a GPU on it, then it's going to find it automatically that it has a GPU over there. That's how you do it, unless someone knows a better way.
Yeah, so if there is a GPU in your system, Schrodinger will automatically recognize it and you can just select it while submitting your job. If it's not there, you cannot run it, first of all, in Windows. In Linux only you can run it. And yeah, so that's all I know. Okay. So, okay, so the next question is, I'm working on Ubuntu. So can we run files on that for MD simulation if we generate the file from Schrodinger software? How to do that?
Yes, the Ubuntu is Linux machine, and if you have a GPU, then you can run it directly on Ubuntu. So it's going to do it automatically for you. If you have any issues running it, send us an email and we can figure it out. Yeah.
So if you have a Linux machine, just make sure all your drivers are up to date, and you can try if you have a graphics card that is NVIDIA. Probably it can support Schrodinger software. You can try running it. Right. So the next question is, okay. So the next question is by the same person who asked for if you can use ethanol for your solvent. Is it possible for you to demo that?
Um, mm, well, I don't want to go to the MS suite. So if you want to just look at this one, then you just go to System Builder and do it. But yeah, if you want us to show MS suite, then send me an email and we can look at it later.
Okay. The next question is how to take a snapshot of different time points in order to superimpose.
So the snapshots are, you can just save your structures from, if you have your trajectory loaded here, you can go to file, you can save your structures for the frame that you have. And then once you save all of them, then you can superimpose them later by loading them all in one place. But because you already aligned them to one starting point, most of them are already superimposed. So you don't have to do the superimpose later. And you can just like take snapshots of your structure. You can either save them as image, which is going to be just an image of your workspace, or you can go to file and export the structure for that particular frame. Or you can also go to export here and just structures. You can save them depending on one per step. You can save them depending on what your start ranges and ranges. You can also choose like trajectory. If you want to save them as a trajectory, you can do all of those things as well.
You're
So
not
there are
sharing
options
your
here.
screen. Can you please share your screen and show that?
Oh,
Not sharing the screen.
so if you go to export here, so you have the option of exporting your structures for your trajectory. You also have the option of saving your trajectory. You also have the option of saving it as an image, or you have the option of saving it as a movie. Depending on what you want to do, you can just do any one of them. And because you already superimpose on the reference structure, you align it on a different structure, it's already superimposed. So just click on any of them, and depending on what options you want to choose, if you just want to export the structures, you can just go and export them here, or you can just export as a trajectory as well. So it depends on what you want to do. The same thing for the video and the image as well.
Okay, so the next question is, what is the temporal resolution, which is the minimum time step supported by Desmond?
I've used 2 femtosecond most of the time, but I think it should support any time step lower than that. You should not use a time step more than 2 femtosecond because it's just not recommended. Uh, did anyone use anything less than 2 femtosecond? Pritesh?
You can use 1 femtosecond, even 0.5 also you can use.
Yeah.
It will increase the simulation time.
But yeah, there is no reason why you want to do that.
Yes, yes. 2 femtosecond is very good. So that is the default one.
Okay, 1 second. So the next question is, I assume most people here do not have access to Quadro Tesla Cube workstation. So is there any cloud-based compute resources that are available wherein we can upload our MD job to your server and receive the output?
No, we don't provide any such cloud services. So if you have your own machine or if you have your own cloud access, then you can install it on your services if you have purchased the license.
Right. So you can technically run it on a cloud, but we don't do it for you. Yeah.
I can show the demo of the doc results and how to use that as a starting point for
Oh yeah.
simulations.
Yeah,
Okay.
that'll be great.
Okay. Let me, you can still see my screen, right, Maestro?
Yes.
All right. So if you go to file, and I was trying to do that before, you go to import structures. The mistake that I had was I was looking for the CMS files, but if you just click on import file types here, and you have these different options that are available after your docking. So the one that you want to look at is the post viewer file. So the pv.megz. So just select that, click on open. You're going to have the results loaded into your workspace. Okay. So you have the protein and you have your ligand here. Okay. I have 5 different ligands and I have the protein here. So let me just change the view here. Okay. So I have the protein here. I'm going to choose the ligand here. Now I have a protein ligand complex, right? I have a protein, I have ligand. Now I'm going to click on right click on merge. And I'm going to have a new molecule that is with my protein and with my dock pose, which is here, the ligand which is docked into this particular receptor. And I can just use as a starting point to do my system builder and set up the panel for molecular dynamics and then the calculation. So just to recap, you go to File, you go to Import Structures, you choose the PV file, _PV. You see the PV here, right? And once you load that, you have your protein and you also have the ligands. We just select the ligands that you want to choose, right click on them, and then click on Merge. Okay? So
So
the
if
same
they
way you can do it for
select,
this one.
means they have to be in blue. So do not include, but select them, those two things.
Yes.
Yeah.
Yeah.
So they should be highlighted in blue on the left,
Right.
both of those. And then you have to control and select the second one and then merge.
Merge.
Yeah. And then your entry will come over there.
Any other questions?
So I have one more question. I think you already went over this. That is how to save a video clip.
Yes. So um, let me show you the options that you have for video clips. So you go to Export, click on Movie, and you have the options here. Do you want to have one per step? Do you want all in the range? So start and end. You have different resolution that you can choose. So you have the resolution of the 1280, 1024, the quality of the video, medium, low, high, um, and then how many do you want per frame? So it's 0.04 seconds. That translates to around 25 frames per second. It's usually your regular movie playing speed. So you can use the default options, just change your resolution, select the range of frames that you want to make a movie of, and just click on export, and it's going to save the movie for you.
I think that's all the questions we received. There was a question from me, I think, about the assessment. So you will be receiving an assessment which is nothing but multiple choice questionnaire, and you would be asked to fill it up and send your responses. Once you qualify that, you will receive the certificate. This will be sent to you probably by the end of this week. Um, so that's how the assessment will be done. Make sure that you watch all the videos, because all the questions will be from all these videos. So I'll just share my screen for a second here. So these are the some of the links that you need to know. I think I already went over these announcements before, but just once again, I want to let you know that if you have any emails, if you have any queries, if you're working on something, you're not able to figure something out, you can write to us at ddcourse@schrodinger.com. So the new schedule, there's a slight schedule change. The new schedule is already updated on the website. On the website page for this course, which is schrodinger.com/dd course. So please visit this page in order to see the updated schedule. I already talked about the assessment test. You'll be receiving it by the end of this week. Make sure you read all, you go through all the videos, all the answers you will get to these questions from these videos. The next about the SOC. So again, the registration will end on October 26th. So make sure that you register and pay before October 26th if you're interested in availing the discounted price of $125 for the next coming up session of SOC, which is November 2nd. So if you want to avail this discounted price, you need to register for this session only. There'll be no more session in 2020, and this discount code will not work in 2021 sessions. So make sure that you register. If you don't have the discount code, you can write to us at ddcourse@schrodinger.com, and we will send you the discount codes. You have to have a website account in order to avail the evaluation or the SOC, or to see the online material, training material and tutorials. So make sure that you register on a website and get the website account. The other thing is on Thursdays we have office hours from 4:30 p.m. to 5:30 p.m. This is hosted via Zoom. The Zoom link is on this page, schrodinger.com/dd course. If you're interested in joining these sessions, if you have questions, you can join here. We'll all be present. We'll all be able to answer your questions. You can share your screen. You can show what you're doing, what is the issue you're facing, and we can help you out. I think that's all from my side. Yeah, so I don't have any more announcements. Thank you for joining us today. Thank you for submitting your questions. If you have any more questions, you can write to us. Uh, we'll see you tomorrow at the same time. Have a great day. Bye-bye.
So you can stop the live stream and close the Zoom session.